Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you, and today we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
Here is our third NMR challenge. By the end of this video, we will be able to calculate index of hydrogen deficiency, interpret 1H NMR, and to understand what is 13C APT NMR and how it is different from 13C depth NMR. Before solving the structure, we are going to revise those chemical shifts values for the 1H NMR and 13C NMR again, and this practice will make us perfect. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problems. So here we are just focusing on the aliphatic types of compounds so far. And 1H NMR chemical shift values is also very important to understand shielding and deshielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly deshielded as compared to the primary, and tertiary hydrogens are slightly more deshielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring, such as in toluene. So it is also coming in the same region. Acetylene protons is slightly deshielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR, we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are some chemical shift value for the carbon. When it is primary, so it is coming up to 35 ppm. When it is secondary, it is slightly deshielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. So after revision, now we are ready to take this challenge. So first we will calculate the degree of unsaturation. So this is the formula: 2C plus 2 plus number of nitrogens minus number of hydrogen minus halogen divided by 2. So how many carbons are there? 5 plus 2 plus nitrogen, there is no nitrogen, hydrogen 8 minus 0 divided by 2 is equal to 2. So there are two unsaturations, so it could be 2 pi bonds, or it could be ring, one ring plus one pi bond. Now we will look at the 1H NMR. The 1H NMR looks so symmetrical, and 1.96 ppm there are multiplane and it's corresponding to 4 hydrogen, and therefore we can't determine how many hydrogens are present on the adjacent carbon. Okay, and the second informations we are getting that the same, there is multiplicity 4 hydrogens, and same here is also again n is difficult to determine what is the value of n, but there are only two signals, 1 and 2, so we can say that there are two types of protons. Now look at the carbon NMR. From the carbon NMR there is a small signal at 222 ppm. This 100% sure correspond to the keto group, carbonyl group of the ketone, or it could be aldehyde. So it could be ketone or it could be aldehyde, and there are two upward signal, and we know that this will correspond to CH2. So this compound have only CH2, two types of CH2. So two types of CH2 and 2 plus 1, three types of carbon. So if you try to make a symmetrical molecule having CH2, so let's try to make symmetrical molecules. So this one unsaturation is attributed to the keto group, and let's put carbon on each side to try to make the symmetrical structure. Now we are missing one more unsaturation, so we need to put one double bond here. When we put one double bond, so this will be CH and this will be CH2, but from 13C depth NMR we don't see any signal for the CH, or we can say that the molecule is not symmetrical also, because the molecule will be like this and it is. So if you try to put the structure like this, then how many hydrogens are there? 8 hydrogens, 5 carbons. So this is matching to this molecular formula, satisfying the molecular formula, but it is not satisfying the NMR because it should have only two types of proton, but here you will have this proton, this different proton, this one and this one. So this is not satisfying the 1H NMR. Now what is other possibility? So other possibility is that if you connect this carbon to this carbon and make it cyclic, then you can have 5-member ring, and this ring, one ring will correspond to the 1 degree of unsaturation, and then you can put this keto group here. If you look at this structure, then there are two types of CH2, one is A, another is this one B. This is also A type CH2 and this is also B type, and because the molecule has plane of symmetry, so you can see that you can easily say that the compound has two types of CH2 and therefore it has only two signals, and probably this one is belong to A and this one is B, and there is a keto group. So this is the signal from the keto group, not from the aldehyde. So there is a keto group, and you can calculate there are two hydrogens from this one. So the 2 hydrogen from this, so total 4 hydrogens correspond to this one A, and this one correspond to 4 hydrogen to the B type. So hence the correct structure for this molecular formula is this one. And here is the NMR challenge for you. Analyze this NMR spectra and try to predict the structure of this compound. Post your answer in the comment section and I will explain you the complete solution in the next video.